Imagine a world almost unimaginably different from our own, yet it set the stage for the life we see today. Picture a single giant landmass stretching from pole to pole, interior deserts baking under a fierce sun, coastal reefs teeming with strange shelled creatures, and forests of trees that look familiar but are subtly alien. This is the Permian Period, a long chapter in Earth's history that lasted 47 million years, from about 299 to 252 million years ago. It's the closing act of the Paleozoic Era, the curtain call before the drama of the Mesozoic. Let's step into that era together, slowly, clearly, and with a sense of wonder. Start by picturing Pangaea, the great supercontinent. All of Earth's major land masses had come together into one supercontinent, a land so vast you could walk for months and never see the ocean. Around it stretched Pangaea, a single global ocean, with the shrinking Paleotethys to one side and the rising Neotethys on the other. Mountain ranges built by earlier continental collisions rose high, the central Pangaean Mountains at times as tall as today's Himalayas, though erosion would wear them down through the Permian. With such a continental interior, climate became extreme. Hot, dry summers, freezing winters in places, and seasonal monsoons that triggered enormous swings in rainfall. Deserts spread across the heart of the supercontinent, while wet forests clung to coastal and highland refuges. The Permian climate wasn't static. It began in the shadow of the late Paleozoic Ice Age, a cool phase that had gripped much of the planet through the Carboniferous. For a while, glaciers and cool temperatures persisted. But as the Permian progressed, there was a long-term warming trend with punctuating events, short-lived spikes or dips in temperature tied to volcanoes and large igneous provinces. One notable episode, the Artinskian warming event, saw glaciers retreat and aridity increase. Later, eruptions in what is now southwestern China, known as the Imeshan traps, triggered warming and environmental stress linked to a major extinction in the Middle Permian. And at the very end, the Siberian traps, massive outpourings of volcanic rock, unleashed greenhouse gases on a scale that pushed the world past a tipping point, bringing about the largest mass extinction in Earth history. Life during the Permian was a mix of resilience, innovation, and dramatic turnover. In the oceans, brachiopods and mollusks dominated many habitats, and reefs were built not primarily by corals like modern reefs, but by now extinct groups including bryozoans and certain brachiopods. Ammonoids, cousins of modern squids and octopuses with coiled shells, continued to diversify, though their groups shifted through time. Trilobites, which had ruled many ancient seas, dwindled to just a few families by the late Permian. Fish were present but not yet the star actors they would become after the Permian-Triassic boundary. Groups like lungfish and early ray-finned fishes occupied freshwater ecosystems, while shark-like fishes prowled both seas and rivers. On land, the story is even more dramatic. The Permian was a time when amniotes, animals that lay eggs with protective membranes or retain embryos internally, rose to dominance. Amniotes split into two major branches. The synapsids would later give rise to mammals, and the sauropsids, the reptile lineage that eventually produced crocodiles, birds, and dinosaurs. Synapsids, particularly the early varieties sometimes called pelycosaurs, were prominent in the early Permian. Picture emblazoned sails and lizard-like bodies, creatures like Dimetrodon patrolling river edges and floodplains. Through the Permian, however, more advanced synapsids called therapsids began to replace many of these older forms. Therapsids were more mammal-like in anatomy and behavior. They evolved differentiated teeth, more upright postures, and other adaptations that set the mammal line on a new path. The vegetation of the Permian reflects that shift to drier climates. In the Carboniferous, vast swamp forests full of lycopods and horsetails had dominated many lowland landscapes. But the Carboniferous rainforest collapse, a climatic and environmental crisis near the Carboniferous Permian boundary, fragmented those wet forests. Seed-bearing plants like seed ferns and early conifers became more common. Gymnosperms, plants like conifers, ginkgos, cycads, and the distinctive Glossopteris in Gondwana, spread across drier landscapes. Glossopteris, a woody, seed-bearing plant, formed large forests over southern continents and is one reason geologists first pieced together Gondwana's past. Its fossils appear across what are now South America, Africa, Antarctica, India, and Australia, hinting at a once-connected southern land. Insects, already diverse since the Carboniferous, continued to evolve. The Permian saw early forms of many modern insect lineages. Beetles made an early appearance and began exploiting wood and dead plant matter. Early relatives of flies, true bugs, and other groups continued to diversify. Some insect groups flourished, others faded, and by the end of the Permian, insects experienced their only known mass extinction event. The fossil record shows both an arms race and coevolution between insects and plants, plants developing defenses and insects evolving new ways to feed and reproduce. Amphibians and other early tetrapods also feature in the Permian narrative. Some amphibian lineages remained abundant in suitable wet habitats. Others declined as the climates became less forgiving. Temnospondyls, a major amphibian group, peaked in the early Permian and then dwindled by the middle and late Permian. At the same time, reptile-like tetrapods radiated into niches left open by these changes. Gliding reptiles, featherless but with skin flaps, evolved in some lineages. The earliest known vertebrate gliders appeared in the late Permian, hinting at the creativity of evolutionary experimentation. The Permian fossil record is patchy and geographically biased. Early Permian terrestrial fossils are more common in equatorial and near-equatorial regions like North America and Europe, while the middle and late Permian records are better preserved in places like Russia and South Africa. Because of gaps and regional differences, paleontologists talk about phenomena like Olson's gap, a break or scarcity in the terrestrial fossil record that makes it harder to trace some evolutionary transitions. Still, across the preserved record, we see sweeping faunal turnovers. Early synapsid assemblages give way to therapsid-dominated communities, amphibian-rich wetlands shrink, and reptiles begin to explore a wider variety of forms. Under the sea, continental arrangements and sea level changes influenced marine life. Sea levels were variable during the Permian. Early in the period, sea levels were higher than today, but a significant fall began in the middle Permian, reaching near-present low stands in parts of the late Permian. When sea level dropped, shallow marine habitats, vital for many organisms, contracted. Combined with climate changes and episodes of oceanic anoxia, these shifts stressed marine ecosystems. Many marine groups experienced declines and extinctions before the final catastrophe, pointing to a pattern of compounding environmental pressures rather than a single sudden collapse. And then there was the finale. The Permian Triassic extinction event, often called the Great Dying, marks the boundary between the Permian and the Triassic. This was not a minor hiccup. Around 90 to 95% of marine species and roughly 70% of terrestrial species disappeared. Trilobites, a hallmark of earlier Paleozoic seas, went extinct at this boundary. Reef ecosystems collapsed. Many groups that had dominated Permian landscapes and oceans were swept away, while the survivors became the foundation for the Mesozoic world that followed. What caused such devastation? Scientists point to a combination of catastrophic events and feedbacks. The massive volcanic eruptions of the Siberian Traps released huge volumes of lava, but also enormous amounts of greenhouse gases like carbon dioxide and methane. These gases pushed up global temperatures, altered ocean chemistry, reduced oxygen in seawater, and triggered acidification. There were also cascading effects. Warming could have destabilized methane hydrates in ocean sediments, releasing additional greenhouse gases. Widespread anoxia in the oceans could have promoted the production of hydrogen sulfide, a toxic gas that can suffocate surface-dwelling organisms and harm terrestrial life as well. The timing and relative contributions of these processes remain areas of active research. But the broad picture is one of a tightly coupled planetary crisis. Volcanism, greenhouse warming, ocean stagnation, and biosphere collapse feeding into each other. The aftermath was profound. Recovery took millions of years. In the oceans and on land, ecosystems reorganized slowly. The survivors were mostly small, opportunistic, and adaptable organisms, lineages that could tolerate wide temperature swings, low oxygen, or shifting habitats. These resilient survivors set the stage for the Mesozoic Revolution, the age of reptiles, the rise of dinosaurs, and eventually a world radically different from the Permian landscapes. But the Permian is more than an instructive prelude to later eras. It was a time of real innovation and evolutionary experimentation. the first true conifers and early relatives of many modern plant groups appeared. Early members of the mammal lineage, synapsids, were exploring new anatomies and life strategies. Insects evolved early forms of ecological roles that would shape terrestrial ecosystems for hundreds of millions of years. Even the loss and turnover of the period contributed to the long-term resilience and adaptability of life on Earth. So when you think of the Permian, picture extremes, a supercontinent under a variable climate, ecosystems both flourishing and faltering, evolutionary lines converging toward modern groups, and a dramatic planet-changing extinction event. It's a reminder of Earth's capacity for both creativity and catastrophe, and how life persists through deep time's trials. As we look back across nearly 500 million years of history, the Permian reads like a long, complex story, full of peaks and troughs, innovations and extinctions, climates that warmed and cooled, and a tapestry of life shifting in response. It's a period worth knowing not just for the sensational finale, but for the quieter chapters of adaptation and change that shaped the world we eventually inherited. If you imagine walking through a Permian landscape, you might feel both foreign and strangely familiar. The smell of conifer resins, the rustle of fern-like plants, the distant thunder of thunderstorms driven by massive monsoon systems. And in lowland marshes, the calls and splashes of amphibians in retreat. On distant ridgelines, therapsids roam, the forerunners of mammals, while in the seas, brachiopods and ammonoids spin through the water. Through that panorama, the Permian becomes not just an abstract date range, but a living world, one that teaches us about resilience, vulnerability, and deep time connections to our own planet. Today's story was a walk through that world. If you carry one idea away, let it be this: the Permian shows how Earth systems, life, and climate are deeply interconnected. Small shifts can ripple outward over millions of years, and even mighty lineages can be reshaped or erased by planetary-scale forces. Understanding that past helps us place our present in perspective, and maybe nudges us to pay more attention to the threads that weave the planet's future.